My name is Jim Binnion, and when they asked me to do a demo here, one of the things was to talk about what's next on the technical horizon, and I haven't a clue. So, towards the end of my slides, I've got something that I saw recently that I think may have an impact as far as a technological device in the not too distant future on some artwork, but we'll see. Anyway, it's a pretty cool set of little videos at the end, so if nothing else, hopefully you'll enjoy them. I'm going to kind of quickly run through what it is I do and kind of how I got interested in metal arts and Mokume and what I do in Mokume, and then briefly going to cover some experiments that Steve Midgett and I worked on for about 4 years that are taking patterned metal to basically an industrial scale of production. It was an interesting set of experiments. Unfortunately, I'm not sure it's going to go anywhere, but we did some fun things. And then for a demo, since I've been working a lot with steels and stainless steels lately, we talked about doing a demonstration of etching, doing photo etching on some materials that are maybe a little different than what you're used to using. And I've come across a means of Xerox photo transfer that I think is better than anything I've seen out there at this point. It does really fine lines. So that'll be the demo part. So first, a little background on me. I have always made things. I don't necessarily classify myself as an artist, but somebody once said that they were a maker of things, and I think that really fits with what I do and who I am. And I got an awful lot of that from my grandmother. When I was a kid, my dad was in the Air Force. My mother said that in the 17 years that they were married, we moved 21 times. Wow. So, not a lot of stability, not a lot of places to go and do things, you know, having your own room for, you know, a few months or a year or so, and that was about it. But when I would go to my grandparents' house, you know, hanging out with my grandmother, there was always stuff to do. And she would make furniture. She wove, she baked bread, she did dolls. It was just always something for us kids to do at my grandmother's. And I remember laying around on her living room floor reading Craft Horizons, which was the magazine that is now American Craft. And so she was a tremendous influence on me. When I was a kid in school, I was one of those that would probably now be classified as ADD, but they didn't have such terms at that point in time. And I think my grandmother was a little ADD too, because she was kind of going from thing to thing to thing and back, and that's kind of how I am now. But I owe her a lot, and I miss her. After I went out of high school, I didn't graduate. I got tired of high school and ran around and did a few things, and I got interested in electronics. A friend of mine was working in electronics, and he had this neat new thing called a microprocessor, and this is many years ago. And I want to learn that. Without a high school education and without having a college education, learning electronics was a little tough, but this was just post-Vietnam, and the Navy was willing to take anybody at that time. They didn't care what your educational background was. They were losing people at a tremendous rate. So I joined up with the understanding that I would go and learn electronics, which I did. I went into the submarines because as I got into my training, I realized that I was going to be pigeonholed if I went into the surface fleet. Very narrow specialization, would only do one little thing, and that doesn't really fit with my personality. So submarine service, you've only got about 100 guys on that submarine, and everybody has to do a little bit of everything. So I signed up for the submarine service, and I spent almost 9 years doing that. The top submarine is the USS Groton. That was the first one that I went on. It was brand new when I went on board, and it was quite a change, but I settled into it and really enjoyed a lot of it, and was bored to tears on some of it. And when I had a chance, I signed up to go and do something that I thought was going to be much more interesting, because I had found a group in the Navy that owned the deep submergence vessels, Alvin, Trieste, Sea Turtle, Sea Cliff. These are vehicles that go down to the very bottom of the deepest parts of the ocean. And I was like, oh, Jacques Cousteau, I'm going to go do that. And no, actually that's all a cover story for the stuff that we went and did on the Seawolf. And the Seawolf was a unique platform with a lot of unique capabilities that I'll never ever be able to talk about, but it was an interesting time period. And I learned a lot of very specialized things while I was there, working on one-of-a-kind equipment, working closely with engineers and scientists. And when I finished up with my enlistment, I went to work at a company down in the Silicon Valley called SRI International, that is a contract research and development company, again working in electronics. Back up just a bit. When I reached the Seawolf, we were stationed in Vallejo, California, just north of San Francisco. There was something missing in my life. I'd gotten kind of, not my fill of electronics, but I'd ceased really being, totally absorbed with it. And I was going through the paper one day and I saw this article for a guy named Alan Revere teaching jewelry making classes. And at this point, Alan was teaching classes in evenings and weekends, because his school was actually his production studio during 9 to 5, Monday to Friday. So almost all the classes were done in evenings and weekends, which fit really well with my schedule. So I would go down and take classes in fabrication and casting and all of these various things that complemented some classes I had in high school in basic jewelry making. And so by the time I left the Navy, I had a workshop in my mobile home that I was living in up in Vallejo. And I got out, and my intention had been to go to CCAC and do a metal arts degree. And my wife at the time was in Berkeley doing her engineering degree, and somebody needed to be working. So that's how I ended up at SRI. SRI does a lot of different things, and it's a place where somebody with a curious mind can learn a hell of a lot and participate in a wide variety of things, which I managed to do while I was there. And so that's kind of how I got all into the technical side of my life. Somewhere in there, I found a couple of articles on Mokume that were in the Goldsmith's Journal and Metalsmith. Particularly remember seeing some down at the CCAC library, because I was going down there to look at things in the library there in anticipation of going there. And I decided, well, this looks really neat. I'm going to teach myself how to do this, because there weren't any classes in it. This is 1981, so really it's still in the very early experimental stages of it. But some of the people at Southern Illinois Carbondale and University of Michigan, the Pijanowskis and Brent Kington students had been experimenting with it and had written some papers on it. And I saw one of the papers that the Pijanowskis had written talking about attempts at electric kiln bonding. Well, living in a mobile home, putting a coal forge in my backyard wasn't going to go over real well with the homeowners association there, so I decided to start trying to figure out how to do it with the electric kiln. And for those of you that aren't familiar with what exactly some of the traditional work looks like, here's an image, or several images of the traditional work. The piece that's on the upper left is a suba or sword guard. This is the original style that what we call mokume was done in a kind of real traditional Western style. We have taken the term for a particular pattern and we've applied it to the whole technique. Mokume gane is actually a reference to a pattern, not the technique of making the metal. But this particular pattern is called guri bori, and the fellow who is credited with developing mokume was copying a lacquer technique that was coming in from China at the time, where they would do alternating layers of red and black lacquer, or sometimes multicolored lacquer, but typically red and black, and they would carve it in relief. So as a sword maker, he was familiar with how to bond steels together and somehow managed to figure out how to bond different non-ferrous alloys together and carved it in relief using shakudo and copper to get that red and black color. The suba on the right-hand side is a much later piece. I actually got to handle that at the Museum of Fine Art in Boston. It was an amazing thing to be able to look at. It's not really clear in this image, but if you look at it a little closer, you'll see that there's cherry blossoms floating on water in that pattern. The fellow who did this had a tremendous control over his patterning. And the other thing that was never obvious from this photo, and I'd seen this many times before I actually got to handle it, that's all a veneer. Every single surface of that piece is veneered with the mokume. I have no idea what the core is, but the outside, the inner piercings are all veneered, and the two surfaces are veneered. So on several levels, it's quite an impressive technical feat. The bowl in the middle is actually a sake cup, about 1.5 inches in diameter. A few years after I started doing my ring production, had a client come in and say, "Oh yeah, I've got some of those," and I've heard this from several people saying, "Oh yeah, I got a piece of mokume," and typically they bring me something that's like, no, not really, but it's nice, but it's not mokume. This guy came in with 4 cups that are, and he got them in an antique store in San Francisco for like next to nothing. Oh. You know, it's like, those belong in a museum. Be very careful with them. But I convinced him to let me photograph them, so I've got a whole series of photographs of those. That's very nice. The 2 pieces below are kazukas. They are the handles for a little utility knife that would go actually into the suba. If you see those 2 side holes on the suba, there would be a knife inserted in one of them, and often the sticks that were used to bind up the samurai's hair would go in the other one. So it was a whole little kit. But those handles would often be made to exactly match the suba or the other ornamentation on the sword. So anyway, they're quite beautiful little pieces. And if you ever really want to see amazing, amazing metalwork, try and get close-up view of some of these pieces that were done for the samurai swords. I don't think there's an equal anywhere in history to the metalworking that's done there. So about 1850s, the Japanese went through a great social upheaval that pretty much destroyed the samurai as a class, and the wearing of the swords was outlawed. So all the people that spent all their time making stuff to go on the swords were out of work. And so techniques that were used to decorate the swords were almost totally lost, and mokume is one of them. So by the mid-70s, there were probably like 4 or 5 people in Japan who knew how to do this anymore, and most of them were old men at that point, and their craft association or guild or whatever you want to call it. They don't share information readily, so it was in great danger of dying out. But the Pijanowskis went to Japan to go visit some of Hiroko's family, and while they were there they saw some Mokume, and they tracked down the guys doing it, and they came upon Mr. Tamagawa, and he showed them some of the basics of how to make it. They brought it back to the United States and started experimenting with it. I love this picture of him. He's sitting there in his suit, raising, you know. It's just... And if you ever get a chance to look at Steve Midgett's book on Mokume, there's some really fine pictures of his work. He does amazing stuff with it. But he showed them some of the basics, and they brought it back to the United States probably like 77, 78, somewhere in that time frame. And they and their students had started experimenting with it. The students at Carbondale in Illinois had been experimenting with blacksmithing. They were coming at it from a blacksmithing point of view and had been doing Damascus steel and branched out into doing some Mokume. And actually, their work was the first stuff I saw. Philip Baldwin, Marvin Jensen, and then Stephen Kretschmer was there in Michigan with the Pijanowskis. And this is the stuff that really got me excited about learning how to do it, because at that point I don't think there were any pictures in the United States of the traditional work. So Marvin is really responsible for an awful lot of what we do now in Mokume, because he developed some of the modern tooling to do it, and I'll show you that in a moment. But quickly just show you some of the things I'm doing. This is about 90% of my work here, is wedding rings. So these are, I mean, probably of that, 90% of it is simple band rings, like the one in the upper left. Occasionally I get requests to do things that are more interesting, and like the one with the tourmalines, the upper right. But that's the majority of what I do, is wedding rings.
Can you ask questions during
Yeah, you can jump in if you have.
I have a question. With band rings, Mokume, you're not doing a sheet, are you?
It's fabricated. Yeah, it's been up from wire stock. Yeah.
It is from wire stock, because when I look at your website, it looks like it's a continuous pattern.
One of the big tricks, challenges in doing Mokume rings is to try and come up with a way to butt the ends of the ring together in such a fashion that it doesn't create a really strong discontinuity in the pattern. And I'm not sure. None of these rings are showing that area on my work, but I do some things to try and hide that. And everybody who's currently working in the Mokume wedding ring, or I shouldn't say everybody, but most of the people who are working at, say, the upper tier of it, if you will, have developed their own particular way of approaching that, and that's kind of a signature piece for what they do. So the way I do it is a little different than, say, George Sawyer or Steve Midgett and Chris Plouffe. Everybody approaches it in a little different fashion. This is the stuff I really love. This is copper, silver, and brass, and the patterns and colors that I can get in the copper alloys. This is what really attracted me to it. The unfortunate thing is you cannot make a living selling this stuff. You get a lot of, I love it, but my customers just don't understand it. When you say copper or silver or brass, it's hard to find somebody who's going to pay hundreds, if not thousands of dollars for the work. You do the same thing in gold and you can charge almost anything you want for it. But, you know, a piece that has, that little ring box down at the bottom, you know, there's probably 4 times the work in that than there is in making a wedding ring. And I can charge about 1/4 of what I get for a wedding ring for that box. So it's one of the unfortunate realities of trying to make a living in the metal arts, is that if it's really labor intensive, it's very hard to make enough money to make a living. And about 10 years ago now, I got invited to do a show with the Metals Museum in Memphis. And I got a year's notice on the show. The show was called Knock on Wood, and it was an exploration of American Mokume artists. And for years when I had been exhibiting, people had said, well, if you could make anything you want out of Mokume, what would it be? And my answer was always a teapot. And so, okay, I have a year to try and figure out how to do this. And to date, this is my first, my largest, and really my only piece of hollowware.
How big is it?
It's at the band in the middle, it's just shy of 6 inches, so in diameter, and it's, you know, a little over 9 tall, I guess, with the bail. So I'm glad I had a year. It took a long time to do this. The sheet to make the top and bottom, each of those sheets was getting close to 8 inches square. And you know, I have kind of a standard rolling mill like most other studio metalsmiths that's only around 4 inches wide. So that's hand forged sheet. So, you know, I pushed it as far as I could with the rolling mill, and then it was, you know, a 2-pound sledgehammer and anvil and forging that sheet out. And as a result, it's actually kind of thick. It started out at 18 gauge, which is maybe a little on the heavy side for starting a piece of hollowware that size, but I was tired of forging it. And it was made from 3 pieces, 3 individual billets of Mokume. Top and bottom each took up most of a billet, and then the spout, handle, and base and stem for the lid were all done from the 3rd sheet. Combination of using a hydraulic press and hammering to form everything. The spout was formed roughly and then forged on a low melting point alloy that melts basically in boiling water. It's called woods metal. The handle was a single spiculum that was then cut in half, and the ball was inserted in the middle. It's a great piece. I only had it for a very brief period of time. I had it, got it photographed. It went off to the museum, came back from the museum. I was headed to ACC Baltimore. It was in my booth at ACC Baltimore. Had a lady named Leslie Farron come up and say, I'm doing a teapot book. Would you have any photos for it? And I said, sure. So I sent him the photos, got in the book. She wrote me a little while later, said, we're going to take an exhibit on tour. Would you be willing to send the teapot on tour? I said, sure. It never came back. She sold it. She had wanted a price for it, and I gave her a price for it, and she sold it while it was on tour. So my wife is still pissed at me because she thought that was going to be the beginning of a tea service. But one of these days I'm going to get enough time to do another one. So traditionally the lamination process was done in a charcoal forge. You got to remember that in the late 1600s, actually up through the beginning of the Meiji Restoration, 1850, The Japanese didn't have industrial tools. They didn't have rolling mills. Japan was a closed society. Europeans weren't allowed even on the main land except in one city. And if they went outside of the gates of that city, they could be killed on sight. We're a very closed society. So when they were taking and cutting this sheet and stacking it, that's all hand forged sheet. And to make it flat, they spent days working it with stone to sand it flat. So it's an amazing thing that they managed to make this work at all. But anyway, they would cut and stack sheet, clean it. The top and bottom plates were iron or some form of steel. They would wire it together with heavy wire. And then it would be placed in a furnace or a charcoal forge. And it would be heated up to the point that everybody here is familiar when you start melting silver and it's still very solid, but as you keep putting the heat to it, all of a sudden you see this mirroring on the surface, shiny. That means that part of the silver is becoming liquid. Still majority of it is solid, but you're starting to get a little liquid in the matrix. Well, that's what you would look for in this case. You would be looking at the edge of that billet, and you would be looking for at least some of the alloys to start showing that shininess. Once you saw that, you'd try and hold it for some brief period of time, and then you'd take it out and you'd forge it to consolidate the bond. Well, when you first put those sheets together, I don't care how good you are, back in ancient Japan or in modern, using all the tricks and tools that we have available with us today, you cannot get more than point contact on two surfaces coming together. If you look at it on a microscopic and then on an atomic level, it's giant hills and valleys. It's not a flat sheet, even though it looks like a mirror to us. So when we're asking the actual atoms to jump back and forth across that boundary, there's a big gap there. So when they would heat it up and start getting some liquid forming, the liquid would flow between the sheets via capillary action, just like soldering. And once they saw that shine and they were able to hold it for a certain period of time, that would allow them to get the bond between the sheets. And it caused a lot of confusion early on because people were trying to figure out how they soldered it together without any solder. But it is really a lot closer to soldering than what I'm actually doing in my studio now. One of the drawbacks to this is that the liquid that flows out of the matrix to go along that capillary attraction between the sheets leaves voids in the matrix, so you have a very weak metal matrix left behind, and that's why you have to forge it to close up that matrix and to heal those openings up. And once it's cool, if you would look at it with a microscope and careful examination, you would actually see the two parent layers on either side, and you would see a third material, just like a solder bond, but very thin between the sheets. So the modern technique, probably the biggest single change was Marvin Jensen's invention of the torque plates. And they're a way of bolting things together rather than using the wire to hold everything together. And this is an example of what that would look like. You still don't have intimate contact between the layers, but you've got a lot of pressure now on the stack. You can't put pressure on it with the iron wire. So they were still firing it in charcoal or coal forges when they were doing this initial development of it. And I didn't have a coal forge. After trying several different things of painting all kinds of goop on the edges of the sheets and mixtures of flux and glue and charcoal and things like that, that never really worked very well at all, I got the idea of putting it in a box and filling the box with charcoal. At the temperatures that this is heated to, any oxygen that gets in there combines with the charcoal, makes carbon monoxide, which is a nice reducing gas, so it keeps everything very clean, and it will actually scrub the oxides off the surface of the metal. The carbon monoxide really wants to turn into carbon dioxide, so when it sees a molecule of oxygen attached to a molecule of metal, it'll actually strip that molecule of oxygen away from the metal, which leaves the pure metal, and now you've got carbon dioxide. So if you hear somebody talk about a reducing gas or a reducing atmosphere, that's what they mean. It is reducing the metal to its pure state by stripping the oxygen away. So again, same thing, not too good a contact at the beginning, but because we've got pressure on it, and these bolts will keep the pressure on it as we heat it up, as the metal starts getting soft and plastic as you increase the heat, the surfaces start coming together. So now, instead of having to take it up to the point where things are actually molten, you have intimate contact between the layers, and the atoms will actually jump across between the sheets. As long as they're clean enough and you leave it in the furnace long enough, you can actually grow crystals across that boundary. There we go. So this is a micrograph of a lamination that I did that is 14 karat red, 14 karat yellow. The area that you can see that looks like somebody airbrushed at the lower limit of the 14 karat red is actually the diffusion of some of the elements in the 14 karat yellow into the 14 karat red. The dark line across the middle is actually an etching artifact from the preparation of this. They go progressively finer sheets of, basically sandpaper into diamond compounds. This is mirror polished, and then it's etched to reveal the crystal structure, and the etching tends to attack in a particular direction on crystal faces, so it actually etches that line, but it's not a defect or an actual line in the surface. It's just what happens when you etch it for this preparation. You also notice the huge difference in crystal size between the 14 karat red and the 14 karat yellow. This is one of the reasons that 14 karat red is a little more difficult to work with than 14 karat yellow, is these large crystals. So one of the problems of being inside of a box is you can't see what's going on inside of there, and if you don't get your temperatures right, if you don't understand what you're stacking together and what temperatures they're going to melt at, what temperatures they're going to melt at with the alloys that you form when these atoms start jumping across those boundaries, you can end up with something like this, where it melted while it was in there rather than staying as one solid piece, and kind of waste a lot of time and effort, not to mention money given today's metal prices.
Can you redo it?
That just goes into the goes to the refiner. That's a total write-off. Well, let me say, you could probably make some form of art project from it, but
what metal is that?
That's silver and copper. And so to learn how to identify what's going on, this is something called a phase diagram. You may or may not have seen this in, say, the back of Tim McCrate's Complete Metalsmith. They show up a few other places. Metallurgists use this to try and define the behavior of two metals. This is what they call a binary phase diagram. Two metals. Over here on the left-hand side, or I'm sorry, on your left-hand side is silver. On the right-hand side is copper. The weight percent copper goes up across the bottom. The temperature goes up on the vertical axis. The little Greek letters there indicate phases or crystal structures, different crystal structures. Silver copper forms two distinct crystal structures, one they call alpha, one they call beta. Most of the silver that we work with is majority alpha because it's very high in silver content. but there is a trace amount of beta in there. This is what makes sterling silver harder than silver or copper alone. You have two different crystal structures. They don't mate well together, so it makes it more difficult for the metal to be moved because these different sized crystals don't want to slide across each other easily. When you want to read one of these, everything that just colored, the little alpha and the alpha plus beta and the beta, those are all solid at the temperatures that are indicated on the vertical axis. The indication of the L tells you that it's some liquid, and in this case we've got alpha plus liquid and beta plus liquid. So back when we're heating it with the torch and we see it start to shine, over here on the sterling silver side of things, that's what's happening. You've got some liquid plus the solid. And then up at the top, everything's liquid inside of that boundary. So sterling silver melts at 1670, so you can come up on the 7.5% copper at the bottom and find where it intersects the liquid line. That's your liquidus temperature. When you get below 1490, there is no liquid present at all. When you get below 1328, it goes back into two separate crystal phases. And if anybody's heard about age hardening or heat hardening sterling, you have to get it up into that alpha place to get a full softness. If you heat it up to that temperature and quench it, it'll be almost as soft as fine silver. And then when you quench it, it locks it in that single phase solution. When you bring it back down to, say, room temperature and then come up to 500, 550 degrees for half an hour, you'll precipitate out the beta crystals along the crystal boundaries between the larger alpha crystals, and it just basically pins or locks those crystals so that they can't move. That's what makes it really hard. There's another thing that we hear a lot about when talking about molten metals. Everybody heard the term eutectic. It's often used in relationship to solders. It's terribly misused by an awful lot of folks. Its meaning is very simple. That point at 28.1% copper is not only the lowest melting point of silver-copper system, it is a melting point. You don't have that mushy or that intermediate phase. Almost anywhere else you go in that chart, there's a range, a melting range. So pure metals have a melting point, eutectic alloys have a melting point. All other alloys have a melting range. So we had some limitations. The torque plates, did some research on things that we might improve it. One thing, if you choose your materials wrong, say you use stainless steel bolts, they expand at a greater rate than the metals in the stack. So instead of holding everything nice and tight when you heat it up, it all gets loose. Learned that one the hard way. It doesn't apply pressure uniformly across the whole face. The pressure falls off at the edges. It's greatest in the middle and gets less towards the edges, so the materials don't get held as tightly. So we talked about, a student of mine and I talked about a way to try and fix that, and that was to maybe try and contain the whole billet. And that has a lot of advantages. And so we embarked on a research project to try and figure out how to do this. You can do it in a laboratory hot press. I didn't have the spare $75,000 laying around. This is a vacuum chamber or a controlled atmosphere and then a hydraulic press mated together. So you can put something in there and put it under pressure in a controlled atmosphere or a vacuum if you so choose. Pretty spiffy, but very expensive. A guy named Ian Ferguson designed a similar type of thing for the studio goldsmith, but still an awful lot of money for a specialized piece of equipment. And we thought we could do it just by choosing materials properly. So by understanding the differences in thermal expansion between the bolts, the torque plates, and the metals that we're trying to bond, we chose a series of alloys that, for the torque plate system, that had less thermal expansion than silver and copper. The bolts have less thermal expansion. And that blue image plug at the top is something that we want to have a really high thermal expansion, so that as this heats up, it's increasing the pressure on the stack. And on paper it looked like it would work, so we put together a research project and we built it. And we did a series of experiments with metal supplied by one of the large metal refiners, and they did all the scientific micrographs and things like that to look at our results. But the end result was it worked pretty well. If you look at the top, you can see this is a typical billet fired in torque plates. That's actually a pretty good stacking arrangement. We haven't got too much overhang here and there. But one of the big problems when you're working, especially in gold, is to trim that edge back to get those all nice and flush after it's bonded. You can lose 25 to 30% of the mass of that billet just removing 1.5 millimeters around the periphery. So even when gold was $300 an ounce, that was not so if you look at the one on the bottom and look at how it's filled the cavity, you don't have that stair-stepping or jagged edge. That's a great advantage. And I don't know if you see these spots here, the pressure increased so greatly inside of that system that the red gold actually extruded out between the gaps in the torque plate. So we got the pressure we were looking for. Yes?
What was the metal that expanded that you used?
Okay, the whole torque plate assembly, except for the expansion plug, was made from Inconel 718, which is a nickel chromium super alloy. It's used in jet engines mostly. You can actually find, down at Boeing Surplus, you can find pieces of it because it is used in jet engine manufacturing. It's probably most closely related to stainless steel, but it's mostly nickel rather than being mostly iron, so it's a nickel alloy. The expanding plug is actually a piece of stainless steel. It's a A286, and it's just a high temperature stainless steel, has a very high thermal expansion rate. So, got a lot of the Mokume all straightened out, and a couple of years ago Steve Midgett came to me and said he had an idea for a way to produce patterned metal on a larger scale. You know, we put a lot of effort into making these little tiny billets, and that's great, but there's a lot of time and effort in doing that. So could we do it bigger and do it in a more cost-effective fashion? And so he came up with the idea, the basic idea, and came to me to see if I wanted to partner with him and try and work out the details of this process. And what we were doing is hot extruding metal. So this is like, the best analogy I have is opening the cap on a tube of toothpaste and pushing on it, okay? And I'll show you some videos. That's what we're doing with metal. Big presses and lots of force and high temperatures. So you've got a container. It's got an opening in one end that a ram goes in, and it's got a smaller opening at the other end that is the die. If you apply enough force, the metal will squirt out of there. Well, trying to do it cold is really difficult with metals, or most metals. Lead is actually done cold. Aluminum can be done cold, but almost everything else you're going to be going with heating to make the metal softer so that you can push it out.
How would you stack
Well,
this?
that's, I'll try and show you a little bit of what we did. That was one of the advantages we saw in this, is that we could build a very precise package. And if you think of it like Millefiori glass, you know, where they're stacking different rods in different shapes together and then fusing it, and it stays the same no matter how far you draw it out, we can do the same thing in metal. So that's one approach, is to just basically build an end-on pattern and extrude it. So, you know, this is just a rough idea of kind of mashing everything together and putting it inside of a canister, and that canister then goes in the extrusion press and it's compressed. You suck all the air out of it because you don't want to have air bubbles in this as it goes through. If you do, it's quite exciting. It makes a very loud noise. And it typically also means a totally failed extrusion. This is a canister that's getting ready to be assembled. The annular stack in the middle there is 2 different grades of stainless steel that have been formed into a pattern and then put in a hydraulic press in a die cavity to consolidate it. So they make these little donuts. The donuts are stacked up, and then they're going to go in the can, and that rod over on the left-hand side, upper left, is going to go in the middle. The thinner sheet metal tubes go between the rod and the middle of the annular stack, and they go around the stack. They kind of act as protecting layers to keep the can from touching the payload. And this all gets welded together. The box that this is in is a totally inert atmosphere. You can see there's a rubber glove sticking out there. You actually work through these rubber gloves into this box. The box has no oxygen in it. It's less than 1 part per million oxygen in this box. So when we assemble everything, it's very free from oxygen. Because if we do the welding on it and there was any oxygen in there, we would oxidize the metal greatly and probably keep it from bonding. So there's the assembled can. And that can is then evacuated, and the tube sticking out of the front of it is pinched off and welded to seal the can. Now this is a small extrusion press. This is a 700-ton press. And you'll see in just a moment a guy in the background will come over and he'll open the furnace. You won't actually see the furnace, but you'll see their faces lit up by the light coming out of the furnace. And what I love about this video is, watch this guy, okay? He's got a glove on and he's pushing that thing into the press. That's 2,200 degrees Fahrenheit. Boom, that's the extrusion, that long. And that can is 3.5 inches in diameter, 14 inches long. On the other end, it's now 1.25 inches in diameter and about 7 feet long. Yeah, the whole thing is pushed through. There's actually a follower block, which you didn't see. It gets pushed, sometimes gets pushed through as well, so you get a complete rod. But it's one of the things that happens when you do this is the temperature actually goes up quite a bit, because you're adding energy to the system when you push it. These are examples of the extruded rod, and in the middle you see an example of what happens when you add heat to something that's already a little too close to the melting point. Towards the end of that, one of those middle rods, you see how it looks like something's a little strange with it? Well, that's a whole bunch of silver that melted when it went through the extrusion press, and the can couldn't contain it because it was liquid at this point and it broke. But we did a lot of different experiments and came up with some really interesting combinations. You can stick things together this way that you can't normally do, like titanium to stainless, platinum to tantalum, gold to tantalum, gold to titanium. So it's pretty nifty. And that's the rear end of the extrusion.
Where's the factory? Is that yours?
No. That's the extrusion presses are like, many hundreds of thousands of dollars, if not millions of dollars. So we hire somebody, we hire somebody to push a can for us.
So that's like a sprue right there, and then you just refine that?
Well, yeah, if it's got metals that are worth refining, you can go ahead and refine that. This is one of the drawbacks to working in non-precious metals, is that even though you've got a lot of time and money in this, that's scrap as far as anybody's concerned, so they're not even going to pay you for it, really. So we've tried a few things to make use of that butt section, because it's thoroughly bonded even though it didn't go through the press. It's had enough work put into it that all the layers are fused there.
Can you press it to sheet?
We made some sheet out of it. We did a couple of different things with it. You can use it for doing larger three-dimensional pieces.
Could knife makers be interested in it?
We had a lot of people interested in it. The problem is that it's still expensive to do. And we ran into a lot of resistance. We chose a beautiful time to start a new business. What was it? We started in, well, we really got going in 2007. So we did get a customer or two, and one of them said, well, we really like what you're doing, but it's got to be cheaper because, we're making, this company is the largest manufacturer of titanium rings outside of China. And they had invested in a process of bonding two materials together, but the people weren't able to deliver the material at the volume that they needed. So they found us and they said, okay, can you do this? And we said, yeah, we can do it, and this is what it'll cost. And they said, okay, well, we can go with that, but we need like a lot of it. And it's like, okay, yeah, we think we can do that. So we went from 3.5-inch cans to 6-inch diameter cans that are 30 inches long, not really understanding how hard it was going to be to scale up. So when we had been using like 50-ton press before to consolidate things, now we need a 200-ton press to consolidate it. Great deal on eBay, though, by the way. That's a $50,000 press that we got for $5,000. I had to put a little work into it, but not too bad, all things considered. The glove box. This is something that I had actually bought before Steve and I started working together. Another great eBay deal. $700 for this thing. Cost me more to have it shipped to my studio than I paid for it. Difference in definition of working from my definition of being in working condition and their definition of being in working condition. So I probably invested at this point close to $15,000 in making it working condition. But if you want to go out and buy one today, that's over $100,000. So I think I still got a good deal, but it was a lot of work to fix it up. But the chamber, there's this area here on the end, we can put things in and out of the chamber without losing the atmosphere. This is an airlock. We can put things in there. We can pump the airlock down and then backfill it with argon, put it into the chamber. Here's a can. We could no longer like push stuff into the can. We had to use a hydraulic press to push things into the can.